Hello, so today we're going to be doing chapter 10, temperature and heat. I know, bear with me, you're used to this by now. Okay, let's go on. So what are temperature and heat? Well, we kind of all have a feeling for what temperature and heat is, but of course we're going to define that much more precisely in this class. So, okay, what is temperature? So measuring temperature, right? Two objects are in contact with one another long enough, the objects have the same temperature, right? Well, we know that heat flows from areas of higher temperature to areas of lower temperature, right? So we all know that. And eventually, if there's two objects that are different temperatures, but they're right next to each other or touching each other, they will become the same temperature, right? Thermal equilibrium, because heat will have flown from one object into the other. All right, and we're going to talk about two different temperature scales, right? We've all heard of these, but of course we're going to break this down quite a bit more. So we all know in the United States we use Fahrenheit most commonly, right? Freezing is 32 degrees, boiling is 212 degrees. There's a guy named Fahrenheit that developed this system. Another person named Celsius developed this system. Here, water freezes at zero degrees and boils at 100 degrees. They use water because there's water everywhere. Humans are used to water, so they define those temperature systems based on water. Now, here's something you're going to have to be able to do for the test: is convert between temperature, right, centigrade to temperature Fahrenheit. If you want to convert to Celsius, you take the temperature in Fahrenheit minus 32. Notice that this is in parentheses, times 5/9, right? To get the temperature in Fahrenheit, if you have the temperature in Celsius, you do 9/5 times the temperature in Celsius plus 32. Notice there's no parentheses here, okay? Yeah, and at minus 40, interestingly enough, they're both the same. So that's just kind of a cool thing. Minus 40, same no matter Fahrenheit or Celsius. Yeah, and here's just some history. Yeah, is there such a thing as absolute zero, right? Because can you keep going down and down and down in temperature? Is there a zero where molecular motion stops? Yes, there is. There is a zero. And here's an experiment where they show based on pressure that you can get to absolute zero. But essentially what it shows is that if you have different gases and you plot their pressure versus temperature, you can extrapolate down. There is an absolute. So it's minus 273 degrees Celsius, centigrade. That is absolute zero. Or this is 0 degrees Kelvin with a K. So 0 degrees Kelvin is minus 273 degrees. It is a zero temperature. Okay? So to convert, if you have the temperature in Celsius, you convert it to Kelvin, you you add 273 degrees to it, and that gives you the temperature in Kelvin. This Kelvin is what scientists use most frequently. When I did my graduate work, everything was done in Kelvin. So, yeah, can anything get colder than 0? No, things don't get colder than 0, right? Can absolute 0 ever be reached? Well, no, you can get real close, but no, you're not going to get to 0. So. Okay, so now we're going to talk about some things that we're very used to in our normal lives, but of course in physics class we're going to break it down and define it much more precisely and put numbers down there, right? Specific heat capacity. This is how much heat objects are able to hold, right? Here they show you're pouring cream or milk into coffee, right? Everyone knows that will cool it down. But what's interesting, if you were to put the same amount of, say, steel shot into that, so if you were to put the same amount of steel shot is little BBs of steel into a hot cup of coffee, or put the same amount of milk, the milk is going to cool the coffee down much more because water, is able to hold a lot more heat in it. That's the specific heat capacity. Okay? And you're wondering, well, what is heat? Well, heat is energy. So you can define heat in joules, which you're used to. You can define it in calories. Now, the calories that we did in our stair lab, those were food calories. Those are actually different than the calories we're going to be talking about today. The food calories are 1,000 calories, actually. And here they're just showing heat is the flow of energy transfer between objects, right? So it's energy transferring between objects. Literally what heat is, the molecules are vibrating. They have energy and they're pushing against each other. And that is literally what heat is. If you have a hot liquid, hot water, the molecules are moving. They have a lot of energy and they're vibrating quite a bit, and that's what heat is. There's energy in the water, and you can measure that temperature, because when that's happening, the temperature of that water will increase. The same with a gas. The molecules are moving a lot more. They have a lot more energy. That is what's happening at a fundamental level. Yeah, so the definition is the amount of heat needed to raise its temperature. That's how you define the specific heat capacity. So to change 1 gram by 1 degree Celsius. Notice here they're using grams. That's okay, as long as we're not going to use kilograms. Here we're going to use grams, and then all of our units will stay in grams. So the specific heat capacity of water, right, is 1 calorie per gram degrees Celsius. It takes 1 calorie of heat to raise the temperature of 1 gram of water by 1 degree C. So this is the best definition. And then other objects, other substances will have different amounts of heat to raise the temperature of 1 gram of that substance by 1 degree C. And that's what defines the different specific heat capacities of different substances. However, water, it's 1. So the standard is going to be water. Then other substances will have a greater specific heat capacity or a less specific heat capacity. Yeah, so you can calculate how much heat must be absorbed by a material to change its temperature by a given amount. So Q is a quantity of heat. Q is energy. It can be in calories. It can also be in joules. We're used to those units, right? Mass, that's the mass of the unit. It's going to, here typically we're going to use grams. Specific heat capacity, that's what we just learned, right? Different materials have different specific heat capacities. For water, 1 calorie, right, of heat, right? It takes 1 calorie of heat to raise the temperature of 1 gram of water by 1 degree C. Different substances will have different calories to raise 1 gram of that substance by 1 degree C. Okay? So this equation is simply the mass, specific heat capacity, and there's tables. You can look this up for different substances. You can get those numbers typically from tables. This will be given to you. C will be given to you. And then a change in temperature, right? So it's a pretty basic equation. I'll be doing equations for chapters 9 and 10 in a separate video this week. There weren't a lot in chapter 9 actually. So. Okay, and this is just showing, oops, let me go back. Let me go back to that, what happened? Okay, so here's just showing that if you have a temperature difference, heat will flow. So here Q, right? The heat is flowing from one object to another. Oops, I did it again. Yeah, so heat is the actual energy, right? And then temperature is just the measurement of that energy, and it's an indicator of direction of flow, right? So they are different. Heat is the energy, right? Okay, so let's get into phase changes. Phase changes is when you have, say, water ice, it melts, so that changed into water, liquid water, and then if you heat that water, then it will boil. So that's another phase change. So you can change it from a solid, which is ice, to a liquid, to a gas. So those are phase changes. By the way, what's interesting, you know, when you're boiling water, so the temperature of boiling water is 212 degrees. The temperature does not change. So increasing the amount of heat, you know, and there's more bubbles coming out of boiling water, it does not increase the temperature. It stays at 212. All you're doing is you're boiling off the water quicker. So tell that when you see someone, oh, I'm going to cook this faster. No, it doesn't work that way. Boiling water is at 212 degrees Fahrenheit, 100 degrees Celsius. Very interesting. Yeah, so latent heat, it's the energy that goes into the change of the phase of that material. And there's different, right? Like you know, on Hawaii you see molten lava. Well, that's rocks can melt, right? On other planets, on Venus, for instance, lead, right? Lead is a metal here on Earth, but on the surface of Venus, lead is a liquid, right? So different objects, they can change phases just depending how much heat you happen to have in your particular environment. So, yeah, so here it is. The latent heat of vaporization of water corresponds to the amount of heat needed to turn 1 gram of water into steam. So this is how they define it, right? Scientists want to quantify, they want to have definitions so you can compare other objects. Other objects change phase too, right? You can have liquid water, you can have molten rock, right? Lava. There's things that are typically gases in our environment, say methane. Methane is a gas in our environment, you know, natural gas, if you have a stove, it's a gas. But if you go to some of the outer planets, methane is a liquid because it's so cold there that this gas is now turned into a liquid, right? So it's all relative. And here's a problem. I've done the homework problems we're going to do. Like I say, I'll be doing the problems in a separate video later on this week for both chapters 9 and 10. So we'll be doing that. Now this is interesting. Here they're just showing that if you do work, say here on water, you can actually raise the temperature. This is something that, you know, with our senses, you would have to do a lot of work to raise temperature. So that's noticeable, but this is representative that yes, in fact, doing work, turning a paddle in water will actually raise the temperature. You know, we're used to friction and stuff. We've all seen, you know, these survival things where you can start a fire by you know, rubbing a stick on another stick, and that friction can cause, well, you're doing work, right? And you are causing heat to be incurred in that substance. So here it's you would have to do quite a bit in order to notice that with our senses, right? You can measure it with a fine thermometer. So yeah, when you're drilling, those of you that have ever used a drill bit, right? They get really hot. They get really hot. Any kind of thing like that, heat. Anytime you have friction, just my hands. I can feel my hands get warm just by doing that, right? So I'm doing work. And then, so you can see where this guy is, Joule, right? We have that that quantity Joule. Well, it's named after a person named Joule. So he found that if you did work, you could raise the temperature of a system. Yeah, and here they devised mechanisms where they were able to measure how much work raised the temperature a certain amount, and they were defining those such a things, right? So here they're talking about work and heat. So they're talking about work and heat in a system. So the increase in the internal energy of a system is equal to the amount of heat added to a system minus the amount of work done by the system. So what that means here, well, let's take the example of if you have a piston inside of a car, an engine, right? In an engine you have a piston, so you have combustion where a spark ignites the gasoline air mixture, right? And so that gets very hot. So now you have energy in that system. And what will happen, it will push on a piston. So that's the work done. You have an increase in pressure because it's hotter. That pressure pushes on a piston, right? It goes down, and it has a crank, goes in your transmission, there's a drive shaft, it turns your wheels, and you go, right? But there's also heat. There's also heat that's incurred. Well, that's kind of a waste product. You wish that all of that energy would just go into motion, but it's not efficient that way. So part of that work is done on the piston, so we get usable work, but then there's also other energy that's in a form of heat. So here they're just saying that you will have the total energy of a system, but some of it is work and some of it will be, you know, in this case, heat, right? But it's the amount of heat. And there's kinetic energy in the molecules, right? The little molecules of gas that are expanding. Well, they're hotter now. They have heat, so they have a higher temperature. So they're bouncing against each other now. So each molecule has more kinetic energy, and of course there's millions or billions of molecules in a piston. So it's that kinetic energy, okay, at a fundamental level. So yeah, so the internal energy of a system is the sum of the kinetic and potential energies of the atoms and molecules making up the system. Okay? Okay, and like I say, I'll do problems. Yeah, so here is a good system. Here they're showing, so this is a piston, meaning that this thing here can move, this part here. Here you have, you know, a piston rod. This is a flat part, and the gas inside here can't get out. So if you push it, you will increase the pressure because you're squeezing this gas, right? So that's what they're showing there. Now, yeah, this is a formula that we had in the last chapter, chapter 9. Force is equal to pressure times the area, right? So you have a force, right, going this way, and then you have a pressure, and you have an area of that piston. Yeah, and work will be, of course, force times distance. Here you have D. And here notice the volume of this piston has changed. So you will do a force. Initially, if this piston was way over here, the volume would have been larger, the pressure would have been less. But you push a force, now you're squishing down this gas, so now you're going to have a resistance to that, like gas shock absorbers. Or if you're trying to compress a gas, you're going to have resistance, right? It's going to be harder to push that down. So if you decrease the volume, your pressure is going to increase. Also, if you increase the temperature, your pressure is going to increase. So pressure, temperature, and volume are all related that way. And here, this book likes talking about work a lot. But here, work is force times distance. Force is your pressure times your area times your distance. Okay? Yeah, and they're saying, okay, yeah, so you would define one as negative, the other one is positive. If you have a total energy in a system and some of it has gone to work and some of it has just been in heat, one of those has to be negative, and that's what they're talking about there. So. Yeah, here we're going to talk about the ideal gas law, and we're going to have some definitions, some fancy science names, right? Adiabatic is you're just talking about a system where no heat flows in or out of the gas when you're talking about a specific setup. Isothermal means you have a system where the temperature doesn't change, but your pressure and your volume can. And that can still change. And isobaric, here, the pressure of a gas would remain constant. So in an isobaric process, pressure would remain the same, but then your temperature and your volumes could change. And here they're talking about, this is called the ideal gas law. So what they're showing that pressure times volume is proportional to temperature, and then you have, but it's not directly proportional. There's a couple of constants. One is a universal constant. The other constant depends which gas you're using, what type of gas, whether it's air, whether it's methane, whether it's hydrogen, right? So that's all it is. So they're just saying that pressure and volume are related to temperature. Typically, if your temperature increases, if you have a can and it's a sealed can and you have air in there, if you increase the temperature, well then your volume, because it's a sealed can, your volume can't change, but your pressure is going to increase. So if you put a flame under it, eventually you could burst that can because the pressure is building. Now, if it wasn't a can, if it was a system with a piston, and if you increase the temperature, well now, as it gets warm, that gas will heat up, and then your pressure would increase, but then your volume would increase as well. So that's how, pressure and temperature are related to pressure and volume are related to temperature. They're all related to each other. And then these numbers here, it's just proportionality constants, saying that they're not directly. Never be scared of proportionality constants. There's millions of equations, hundreds of thousands of equations out there where different parameters are related to other parameters, and they change by a certain factor. That's all the N and the K are here. So. Okay, so here is a good example. A hot air balloon is a good example where you change the temperature. You change the temperature, right? So when a hot gas is in a hot air balloon, the pressure, not the temperature, remains constant. So what happens is, because the bottom is the opening on the bottom, the pressure inside the balloon doesn't increase. Like if you had a can and you heated, if this was a can, you had a flame under it, well, the temperature would increase, but so would the pressure. But here what happens is the hot air is able to escape, so your pressure doesn't change. But the gas will expand, right? So the spaces, the distance between the molecules in the gas has actually increased. So there's actually less gas inside the balloon, and since there's less gas, that parcel inside the balloon, that parcel of air inside the balloon weighs less than the air around it, and the balloon goes up, it rises, and that's how it works. Isn't that cool? Right? Play this part again if you want to hear that again. That is cool. That's how it works. Okay, the balloon experiences a buoyant force because the gas inside the balloon is less dense, right, than the surrounding atmosphere. And so that parcel of air in the balloon goes up, and you carry the people in the basket, in the balloon basket. Yeah, there's three ways that heat flows. Conduction, if you have something that's really hot and you touch it, you're gonna burn yourself. So conduction is two things are hot and are touching each other. Convection is if something is hot and something is cooler here, but there's air in between, so the heat can be carried by air. We're used to that. Air conditioning works that way. When you have air, warm air blowing in your house, that's convection. So the temperature moves around by convection, so it needs a gas in between, a medium. Radiation, you don't need a gas. This is like radiation from the sun that gets to us from space. It's just the photon. It's just the light waves, the electromagnetic radiation coming from the sun. That's radiation. Well, you have radiation down here on Earth too. Your microwave oven works with radiation. That's why you put silver on the inside of a thermos, right? Because it can reflect the heat back into the thermos, right? So radiation, it's not touching. You don't have air. It's just infrared rays. If something is hot, it's just infrared radiation is coming from it, right? So electromagnetic radiation is just given off. So here they're showing conduction. Yeah, you have two things, and you have a metal bar between it. Well, that's going to conduct the heat between those two things, right? And what's interesting is, thermal conductivity. That's how easy or hard it is for heat to flow in certain objects. So you know that if you pick up like a metal block and a wooden block, the metal block always feels colder. Or else, even on your floor, if you're walking in your house barefoot, if you're walking on carpet, it feels warmer than when you're walking on, say, in the kitchen, on the tile floor or something. So the tile floor, or in this case the metal block, is a better conductor of heat. And so therefore, when you have it in your hand, you have heat from your hand flowing into the metal block, and it feels colder. Just like when you're walking around in your house on a carpet or a rug, it feels warmer, but when you step on the tiles, now that conducts heat better, and so it's taking heat out of your skin, and now it feels cold. That's how it works. Cool, right? So the metal feels colder. Since contact with the metal cools your hand more rapidly, the metal feels colder. Interesting, right? Because they're both, like, say if these are both in your house, they're sitting there, they're the same temperature. That's why one feels colder. It's taking the heat out of your skin more readily. And here they're just showing convection, right? They're showing a thermos. Thermos has insulation. When you have a vacuum, when you use a vacuum as insulation, well, then only radiation can get across because there's no gas. Things aren't touching. So in a thermos, when you have there's a little vacuum area, well, there's no conduction in this area because nothing's touching. There's no convection because there's no gas, but you still have radiation that can get across. So if you make it silver, then you can reflect the heat back. Just showing how a thermos works. And here's some examples. Right? Why does your car get so hot when it's parked outside in the sun? Well, that's radiation. Actually, in your car, it's like a little greenhouse effect. The light that goes through the windows, because the windows are transparent to normal light that we see, and then it heats up the interior of your car, but the infrared radiation can't get out. IR, we can't see infrared, but we can feel it. Well, that can't get out of the window, so your car heats up inside. It's a little greenhouse in your car. And here they're just showing the greenhouse effect on planet Earth, right? So, light comes down from the sun, hits the Earth, but infrared radiation gets trapped. The more carbon dioxide you have, the more of it gets trapped, right? It just works that way. And that's it, folks. And I'll be doing another video with problems later this week. So.